All right, so this is officially the last part of this control series of problems. So this last part is going to be talking about the idea of a PI controller. We've talked about proportional controllers in the past, which just utilizes Kc, the proportional constant. But as you can tell, the PI controller in the problem statement says proportional integral. So now there will be an integral part of that controller, and we'll see how that transforms into the Laplace domain, how that affects first order transfer functions. We'll, analyze the amplitude ratio and the phase given this first question there. And then for the second part, we'll add that to our first order plus time delay FOPTD model, which we did in the previous video. See how that changes the FOPTD, and we'll actually use this index of a ITAE, integral time weighted absolute error, how to calculate optimum values of Kc and tau is. So what is tau is? So that's relating to our proportional ID controller, or proportional integral controller. So just pi. So I'll move over to the side here so we can get started. Checking. Okay, we're recording. Okay. So what do we start with? Well, what do we know? Let's go back to our closed loop function, since closed loop transfer function, since I also want to do the final value theorem to see that how this differs from the proportional controller. Yeah, so we have our input, some y value, or usually a set point, and this is our controller, or our not controller, but the measuring the set point error. So again, that gives us our error. I might be doing this a little backwards, but bear with me here. So usually we have our error going into our transfer function for our controller, GC. And then usually that was just Kc, and this gave us an output, ABU, the Laplace domain, and then our process GP, which our general form is K over tau s plus 1. Now this was our, this gave us our output, our desired output, maybe big Y. And remember this loop back for our feedback, which went through the measurement device GM. And we simplify this to 1. But technically, when it goes back to this measurement, man, I can't remember the name, but it's measuring the difference between our set point and technically our measurement times our y, where if the measurement transfer function was 1, then it's just measuring this error would be measuring the set point comparator. That's the name. So it compares the y set point minus the y if, again, GM is equal to 1. So now we're interested in seeing how this Kc has changed. This transfer function of the controller is now, so what we're usually used to seeing in our coding in Python, we've seen it as Kc times the error, a direct product of the two. And now we're adding on to this. So it's Kc, so I guess I should label this is the P portion, the proportional controller aspect. And also I should note that we're not in the Laplace domain yet, so this is what it should look like outside of the Laplace. We'll be taking the Laplace of this, so to speak. So it's Kc times, there's an integral here. It goes from 0 to t. Now that t is the time after which the system has ran in response to the input function. In our case, it's a set point, but remember in previous videos, we've done the sinusoidal input. I believe the set point is just a function. We just treat it as, or a unit step function. We treat it as, or sorry, I'm mixing up my words here. So the set point for our case, we're treating it as a unit step function, which helps simplify things. But again, it could be a sinusoidal input. So this integral goes from 0 to t time, any t time where our system has started running, and it's of our error, and this is, we're taking the integral with respect to tau, and this tau variable is sort of dummy variable, if you'll let me call it that, since this error only depends on time. As you can see, it's a direct constant multiplication if we, well, simplifying the integral, and then we multiply it by this term 1 over tau I. And now this term is any controlled variable or a controlled parameter. We decide what it is, and it's also known as a reset time. And the reason why it's called a reset time is for a scenario where we have, let's say, we have an error that is constant, and it reaches some point in time t, where t is equal to tau I. Now, you'll notice that the 1 over tau I is in front of our integral. So the area of this rectangle, again, integral is area under the curve. In our case, it's a rectangle. Since error is constant, we say that this is, the area is error times time, which is tau I. So essentially, error, maybe something like that, error tau I. So now if that simplifies to error tau I, we can take this term here and say it is 1 over tau I times error times tau I. And well, that just simplifies to error. So now our integral action, or our integral portion of our controller, is now just the error. And if you notice, we have a kc in front. So this overall PI controller simplifies to kc times error plus kc times error. So you'll notice that it's called the reset time because it repeats or resets our integral action to the same as that of the proportional controller. So kind of a reset or repeat, however you want to say, but that's why we call it the reset time. So that's the overall gist of the PI controller, the integral portion at least. And now if we take the Laplace of this, well, we can take them separately since there's an addition here. So we know this for, I guess I should label these. So maybe 1 and 2. So the pink parentheses, I know we got a lot of colors, so we'll do this one by one. So for number 1, we know the Laplace, we've done this before, kc times e, the error, epsilon. Well, that's just kc, the constant comes out, and error, we can express as a function of time, but usually we just call that big E. So epsilon, the Laplace of that epsilon variable, and now big E to represent it in the Laplace domain. Now number 2 is a little different, but similar thing. I don't think we've done the derivation, and I won't try to do it here, but I'll just show you what it is so it makes more sense when we do the final value theorem. So that's kc times, what was it, 1 over tau I, integral 0 to t, epsilon for error without the Laplace, not being in the Laplace domain yet, and then our dummy variable tau. So we take the integral with respect to tau, and we see that this is a Laplace of an integral, and we can just say that both of these are constant, kc and tau I. We determine those are again controlled parameters, so we again just focus on this, well, not that, but this portion, this integral. And if you Google it or try to derive this yourself, you'll see that the Laplace of that integral ends up becoming, so I'll put the constants out in front, kc 1 over tau I. That Laplace of, I guess, the purple would be 1 over s times whatever you're integrating as. Or multiplied by whatever you're integrating. So this is epsilon, and we know that integrates to, or I guess the Laplace transform of epsilon, if we move it to the Laplace domain, is now big E to represent that change into the Laplace domain. So now if we combine these expressions here, we'll have in the Laplace domain the control transfer function kc big E plus kc times 1 over tau I s big E. So now you can see that we can factor out two things. We factor out the kc and the error, and now we're left with 1 plus 1 over tau is. So this is actually our transfer function for the controller. As you notice, that error, this error here that was factored out from both the proportional control and the integral control is being factored out because we multiply error against our transfer function here. So that's already included in our closed loop system. So our feedback, I don't know how you want to say, transfer function, our system under closed loop control or feedback closed loop control. So now if we want to do the final value theorem, we look at our, so let me move this to the side here. We look at our entire system once again. So we've done this before, but if we want the overall closed loop transfer function, we take the transfer functions in the forward direction, divide that by 1 plus the open loop transfer function. So that would be, we have, well, now this is different here. I don't know if I can maybe use a number. We can use 3. So this is 3 up here. So I don't have to rewrite it, but that's representing our it's representing our PI controller now instead of just a proportional controller, including that integral portion. So if we want the overall transfer function, we've done this before, it would be, so let me write this out. We have y set point times our closed loop control transfer function, and that is equal to y, our output. So I'll write that down here. We have y set point times g closed loop is equal to y, our output, and then our closed loop control we know is again in the forward direction. So that was GC and GP. So in the forward direction, that's our controller and our process. So GC times GP in the forward direction, and 1 plus the forward or the open loop. So open loop is right before it cuts off here, before the comparator. So that's an open loop since it's not connected. Otherwise it'd be a closed loop. So now we do GC, GP, so the forward direction times the transfer function in the backwards direction, so that we only have GM there, our measurement device, but there could be more. So in our case, GC times GP times GM, the controller times the process times the measurement device. So GC, GP, GM. And notice we have GM is equal to 1, so we could take that out technically, but if we write it here so we know it's there. So now, if we want to do final value theorem, again, we've done this before, but you'll notice that compared to a proportional controller where we actually never hit our set point, as proven by the final value theorem, I believe it was something like KCK over 1 plus KCK. So notice we never hit this numerator, and as we try to achieve a 1/1 ratio by making KC very, very big, we notice the instability since we had our conditions where we had negative 180 degrees and an amplitude ratio of greater than 1 when our system was at, I believe, third order technically. So that was 3 first orders in series, or our 3 tanks in series. So we didn't hit that set point. But now with this PI controller, we actually will. So what's the best way to do this? Let's write, yeah, we can write out our closed loop first. So GCL, we'll plug in our the actual numbers or the representative variables for each transfer function. So we've written GC before. It was, I mean, we can go look at it here. It is right here, what I circled in yellow. So KC times 1 plus 1 over tau I times S. So again, that tau I is the proportion for the integral, I guess, integral action, if you want to say it, like how much are we making this integral affect our controller, and as that error accumulates, how hard are we going to change our control so that it changes our system in response to that error. And the whole reason why this final value theorem works, well, not works, well, we're going to show it algebraically, but, or with our limits with the final value theorem, but the reason why it's better than the proportional controller is that this integral is accumulating error. So that error accumulates over time, and that offset between the set point and the actual output is trying to get rid of that accumulating error. So that way it's not just a direct multiplication of KC times E like what we would have with our proportional controller, but now we're adjusting for that accumulation and error, not just a direct product once again. So plugging in our control, we have, what did I say? Kc times 1 plus 1 over tau is, and then times gp, which we had as k over, I believe it was tau s plus 1. Let me double check that. Our general form, correct? Yep, it's just first order. So again, this is first order final value theorem. So first order with a PI controller. And then we have 1 plus the exact same thing up top here. So I'll just copy paste that. Copy and paste. Move that a little bit. And then times GM. So GM is just 1. So we don't really have to care about that. I can simplify this a little further now. I'll hold off on that. So remember our final value theorem. Again, we've done this in a previous video. So we take the limit of a function. In our case, it would be the y set point. And also remember, again, as another tangent, or I guess aside here, the set point is in deviation variables. So when we see, well, let me write this out. So limit of the function as time goes to infinity, we have the limit as s goes to 0 of the Laplace transform of that, which would be, or I guess the Laplace, not of this function, but the Laplace transform of dy dt, the change of our variable. So let me move this down so we have more space here. And this set point, well, let me finish talking about this differential. So that is equal to s times big Y. So we took the Laplace of our differential times y at 0. So that original steady state. However, since we are in deviation variables, this would be written something like y minus y bar, where y bar is the steady state. And if this is in steady state, the Laplace transform must also be where we have y prime technically at 0. Notice that that's not a derivative, it's just a notation for the deviation variable, and this thing goes to 0 essentially because when we write y prime of 0, we're writing y bar minus y bar. So it's at steady state, where if we subtract steady state from steady state, we get 0 essentially. So that's that whole spiel. So I'll just write it as s times big Y, since we know that this goes to 0. Now we can plug in our transfer functions. So we have y set point and y output here with our general closed loop transfer function under feedback control, or I don't know, you can say it the other way around, feedback transfer function under closed loop control. I think that's the actual correct way of saying it. So if we plug in our values here, we have the limit as s goes to 0. Again, remember this y. I guess it should be technically, oh no, that's correct, y output. So this is coming from here. I'll do this in red. So we have this y, we're substituting in our values, our set point, and our closed loop transfer function. Remember, well, we already have this in the Laplace domain. However, to take the Laplace of our set point here, that is just a unit step function. So something akin to a on and off switch. So maybe we have right before 0, it's, well, before some time, we'll say 0 without a shift. And then after 0, it has an immediate effect. So that is the unit step function. And if we take the Laplace of that unit step function, that is just 1 over s. So remember, we need to include a 1 over s for this y set point, as well as plug in our closed loop transfer function, which is this big thing that we wrote out. So let's start with the 1 over s. So let's not forget our s from the Laplace earlier, and then we have 1 over s. So maybe it might help to plug in what it looks like first. So we had a y set point and GCL. Then we take, I guess technically that's under Laplace. So let me write that. Laplace of our unit step function at our set point, or it is our set point, and then GCL. Now we plug in actual values. So s times 1 over s, and then GCL, I'm just going to copy this whole thing. Save some time here. since I don't think this is actually, I really, well, I know that it's not part of the actual problem, but I figured it makes sense to show it. Copy paste, something like that. Very big. Okay, so now as s goes to 0, we can actually cancel out, well, this s times 1 over s. Now I'll rewrite this whole thing, simplifying. So what we can do, it looks a little funky. First things first, I'll multiply tau I s to this 1. Again, simplifying so that we can actually show that as the limit goes to 0 for s, this will simplify down to 1, which is what we're aiming for since we want it to be equal to our function set point, so that it shows that we actually reach our set point and not some proportion of it with our, as we did with our proportional control. So if we write this, we have limit as s goes to 0. We can bring out this kc over k. Is that what I want to do first? Yeah, sure. So then we have kc over k. Since those are constants, I multiply this fraction, the denominator across, so it's tau I s plus 1 over tau I s. So tau I s plus 1 over tau I s. And then I'll keep this, I don't know, fraction by itself. So that's 1 over tau s plus 1. We have 1 over tau s plus 1. And I believe the exact same thing will happen right here since they're identical. So we have a 1 plus, and then I can just copy the numerator. So let me go down a little bit more here. We have 1 plus, and then I'll copy this down. And what you'll notice here is that we can do some canceling out. If I'm fast enough to show it. Okay. So since they're a direct product of each other, we can actually just remove these parentheses and combine them. So it'd be something like, see, I can just move this over, right? Let me write parentheses first. So parentheses, 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 parentheses. So I'll move this over, something like that. Oh, that actually looks pretty good. And then something like this. Move that extra 1. So now, what else could we do? We can move over this denominator over to this 1 like we did up here, right there. Kind of not really a rationalizing, but having a common denominator. So I now have something very funny looking. So limit as s goes to 0. I think I'll just, what's the best way to show this? I'll keep it as, I'll move this over to the numerator up here. So then you can see how eventually these two will cancel out with these common denominators. So instead of writing out, yeah, sure. So we have kc times k over, what is that, tau is plus 1? Tau is plus 1 over common denominator, tau s plus 1. Tau s plus 1. Right? Then we have multiplying that orange arrow, tau s, oh, this is tiring, tau is tau is, sorry. I forgot my I here, right? Yeah. Where did it go? Tau is times tau s plus 1 plus kck tau is plus 1. Starting to see the similarities here between the numerator and denominator. And now we have our common denominator, which actually matches the denominator and the numerator. So you'll notice that these actually cancel out. And now, to avoid rewriting everything, you know what, I'll just substitute, yeah. I'll substitute 0 in for s here. So after those cancel, come on now. We have, so kck, and then, so substituting s goes to 0, that's 0 plus 1, so that's just 1. and then over, denominators canceled. We go to the numerator in the denominator. So that's s goes to 0. You have 0 times 1. 0 plus 1 is 1 plus kck. And then 0 plus 1 again, so that's 1. So this actually just simplifies to kck over kc times k. So that's our system gain of our process and our proportional control, and that just goes to 1. Now we do reach the equivalent of our unit step function, or not, sorry, not unit step function, but our output is now equal to the change of our, well, I guess the Laplace of our change in our set controlled variable, or essentially, let me just delete, yeah, get rid of all these. It's this thing. We prove that the set point or the output will reach the set point through our closed loop since it's equal to 1. Our final value theorem shows that it's equal to 1 here. So now we can actually go ahead and graph that. I believe we'll be coming back. Should I do it all now? I think it makes sense to go back and forth here. So we can code out the transfer function for the PI controller. So let's do that. Let me run all this. So last time was 2 days ago about, yeah. You can see that. Only thing to mention here is this idea of a Bode function, which I could import now. I don't know why I waited and then ran it all. So I'll do it here and rerun this cell. But this Bode function, which is imported from our class repository in GitHub, it essentially lets us keep everything in the Laplace domain, and then we don't have to switch it out when we code out the Bode plot, since we need to, right here, we substitute s equals j omega. When we use the Bode function, it grabs those, it essentially, excuse me, grabs, it does all these, I guess, let me highlight these. It does all these lines of code, and it gives us the amplitude ratio and the phase. And then you'll also see it gives us a figure, but I guess it wasn't that well coded, or there's some errors there. I know in class I kind of skipped over that, and we just used it as a substitution for the amplitude ratio and the phase. So that's what I'll be doing. I can show how we do it the normal way first to show the differences, but yeah, I think it's all done now, right? So let me rerun this. We have Bode. I'll do it the normal way first, so let me put the iPad on the side. Hopefully that stays awake. We have PI controller with first order transfer function, maybe normal way, previous method, RI. So we got our real and imaginary by doing the, this is the forward loop, right? Or not forward loop, open loop. So I know we've been, usually with the Bode plot, we just graph, we just plug in our functions directly. It's a direct multiplication. And technically that works since GM is 1, so you don't have to include GM here. But I will just in case, well, I will just to show that it does exist for open loop. And then when we do our actual plot of the system, have I done that anywhere here? Something like this. We plug it into the simulation. This is, of course, open loop. Is it open loop? I don't know why it's open loop. It should be closed loop. So, well, see, now I'm getting confused here. It is the feedback loop. I don't know why I wrote open loop. This might have been a previous video, so I apologize for that. When you run the simulation, it is for your closed loop, your feedback control. That's what you're plugging in, and then you have whatever step functions you put in. So yeah, let's actually just start putting this in, and I'm gonna take a little pause here. And do copy paste. maybe plot the actual plot first. Class. Product. Start. So clear. Values. No, we don't have. I do imaginary fonts one, so include G. I'll write it in the GC. Our controller is one how I s plotting it out. Process form how times PM is your simulate this patient higher function other plus or direction simply some Python here. Okay. Oh, ported so two order so polynomial denominator of our numerator that is that hours. Okay, so I don't know how long my mic was swung out like that. That's a little awkward. I think that was only for 5 minutes. Oh boy, so I don't know how much was cut out. That's really awkward. But essentially, I'm going to be reworking this more. I'm going to be doing it with the RI method, the way we've done it before. I'll also do it with the Bode, where we grab the it essentially just does this line of code for us, and we get the amplitude ratio and the omegas, or amplitude ratio and the phase directly. And then right now what I'm doing is, I'm pretty sure that wasn't being recorded or it wasn't being caught by the mic. I'm doing it in the Laplace domain for the actual plotting of our function. It was a PI controller with first order. So we'll see what that actually looks like first. So if we simulate that, GFB, and then we have a unit subfunction, lambda time. We've done this before, so we're just anonymous function for time, and then we have a step function of 1. I think our defaults are 100 time steps, maybe. Yep, and then change of time is 0.1. So I'll write those in case we want to change them. And what happens is that we're getting time values and our output function values. So I unpack those as t and y. And I think we've done this before, so I can just steal a plot of this. I think one of them was oscillating right here. I'll do that. Yep, we did it right here earlier. So this is s cubed. I wonder what this was for. I don't know. I don't remember what it was. I think this was our original. Yeah, for 3 tanks in series, so to the 3rd power. That's why it was oscillating so much. Since I believe at 180, was it passing? Oh no, this is actually stable at 180. So 0.5. Yeah, it's actually pretty stable. But if we change the amplitude ratio, or not amplitude ratio, the KC higher, then of course it would overshoot this amplitude ratio of 1, making it unstable. So again, going back to what we were talking about, this is a really long file. So we're just copy pasting, and what figure are we on now? 6, so 7. Just trying to keep it without overwriting anything. And let me add height is equal to 400, width is equal to 600, just to kind of make it similar to class. So yeah, wow, that is 0 to 60. What is our, did I run these again yet? So this will actually be wrong if it'll take the same k constants value, so. Oh, okay. Interesting. We're overshooting it by a lot, so that's weird. Let me just do it one more time. Yeah, okay. I wonder. You know what? Let's see our Bode plot first. So I don't know why it's overshooting that much, but oh, what am I doing? This is forward direction. This needs to be entirely in the closed loop. So it's 1 plus all of that. And DM is not there because this is the forward direction over 1 plus the open loop. So I don't know. I made this mistake earlier. I don't know what I'm doing. So this should be different. There we go. So it is oscillating. So notice that originally with a first order, do I have that anywhere? Oh, that's second order. So first order, did I even plot it? Come on, man. So I didn't plot it. I don't think it's worth trying to plot here. What is this? Okay, this is for 3. If I do it for 1, it might work. We'll see. Super oscillatory. Okay, anyway, forget I did that. Anyways, so it oscillates for, since we added a PI controller to our first order transfer function, we'll look at our Bode plot for stability here. I think I am jumping the gun a bit for stability, since I didn't do the amplitude ratio stuff yet for our PI controller. But yeah, I definitely am jumping the gun. I don't know. I think I just wanted to code that bad. Okay, anyways. Well, this is what our overall system looks like under a first order transfer function multiplied by our PI controller. So there's a PI controller attached. And if I change this, this should be how fast, this should affect how fast we're changing. So that integral controller, oh, what is happening? So it is unstable at this number. Oh my goodness. I mean, it does eventually die down, so maybe that's too much. What did I have earlier? 0.1? So some oscillatory behavior, since we are adding a order to our first order polynomial, if that's right. Since we multiply, well, you'll see it in the amplitude ratio. Since again, amplitude ratios are multiplied and then phase lags are added. Yeah, I think it makes more sense to actually show that first. Since if I have, well, this isn't even right, but yeah, let's derive the amplitude ratio and phase lag before I start doing the Bode plot. I don't know what got into me there. So anyway, oh, why are you like that? Okay. Now to the actual question. So, what are we doing? First order system will be stable. So we need to prove that it doesn't go to negative 180. And along the way, since we're already here, we might as well do the amplitude ratio. So what is our loss transform of our transfer function for our controller? So we had GC, that was KC, 1 plus 1 over tau IS. So we do our usual transformations, or I guess not transformations, but I don't know, method. So we substitute j omega to get into the frequency domain. So Kc, 1 plus 1 tau I j omega. Now I can rationalize the denominator here. Normally we've been multiplying by the complex conjugate, but it'd be easier to just rationalize the denominator here. So I don't know, rationalize denominator. Oh, I put a period there. So I can look at this fraction specifically, and I can multiply it by negative j over j, and that allows us to simplify this something that'll make the amplitude ratio, or that will allow us to separate the real and imaginary numbers easier. So this would be negative j over, let's see, so it becomes negative j times j, which is negative j squared, and tau I mega. And of course, simplifying further, I'm going to move the j in front, 1, and then negative j squared is negative 1, so this is just positive 1. So that gets rid of itself, and then you have tau I omega. So this is what becomes of multiplying by negative j over j. So now, rewriting our entire field here, you have Kc times 1 minus, so minus j, 1 over tau I omega. Now this is our real and our imaginary portions. So for amplitude ratio, pretty easy. Remember that's real squared plus imaginary squared over under a square root. So we have 1 squared plus the minus 1 over tau I omega squared. So this becomes 1 plus 1 over tau I omega squared. Notice that this is actually squared under a square root, so we can actually take that out. And I am forgetting one thing, that is the Kc. Very important there. So that's not to a Kc root. So let me change that. That's Kc and Kc. Don't forget that. Our proportional controller. Then we take out this squared under a square root. So we have tau I omega. Then under it, we can multiply the denominator across. So then we'll have tau I omega squared plus 1. So that's our amplitude ratio. Notice that Kc is still here. So again, if we multiply Kc to our transfer function under closed loop control, or even in our Bode plot where we had open loop, and remember we saw with our three transfer function in series that were all first order, multiplying Kc, or actually changing Kc, increasing or decreasing by a certain factor will shift our Bode plot for our amplitude ratio up or down by that same factor. So the same thing still applies for this PI controller. Now the interesting part here is with the phase lag. So remember, phase lag is the arctangent or tangent inverse over I over R, imaginary over real. So that was, what was that? Imaginary is negative 1 tau I omega. So negative 1 tau I omega over a real was just 1. So 1. And we can simplify that further. So remember the definition of an odd function, f of negative x equals f, or negative f of x. So tangent is a odd function, so we can pull out that negative. So we have negative tan inverse over 1 over tau I omega. And if you remember from a previous video, I think it was actually just the last video here, part A, we did that earlier where we proved that the phase right here, so since tau omega were both positive numbers, we would end up from 0 to pi over 2 or 0 to 90 degrees. And since the negative's in front, then it becomes 0 to negative 90 degrees. So the same thing applies here, except you're in a fraction. So the inverse would apply for increasing and decreasing tau I omega. So the, I guess, range for this would be negative, or I guess 0 to negative 90 degrees. Now, when you have a greater, I don't know, very big omega, you would have a tangent inverse that would have 1 over infinity, which is essentially 0. So for a very big omega, you would have tangent inverse of 0, which would just be 0. Now, if you had a very small value of omega, tangent inverse would be 1 over a very, very small number, something like that, and that approaches something like infinity. And then the result of that would be pi over 2. But remember, we had the negative in front. So I guess I should put it here too. The negative. So this becomes negative pi over 2 in radians, or negative 90 degrees. So the exact same phase lag with the PI controller is now being introduced. So our PI controller would now be the same as a second order system where we have asymptote at negative 180 degrees. Since remember, again, in that previous video, if we had 2 in series for first order here, you had negative 90 minus negative 90, you would have 180 degrees. And then with our 3 series of tanks that were gravity drained, represented by 3 first order transfer functions in series, you would have negative 90 3 times in a row, so negative 270, which is what we see in our Bode plot. So actually now I think is the time when we plot this out, since I think the question is asking it will always be stable. So we have amplitude that, or a phase lag that never actually reaches 180 degrees. So no matter what our amplitude ratio is, or our KC, it doesn't matter since it wouldn't be unstable. So let me try to see what happened here. We'll do it our normal way. So can take out our, we can just rewrite all of this, right? Yeah. So, and then I will change all of these to the j omega domain. So that's under feedback control. So we just substituted in j omega for our Bode plot. And this would be, so let me do that first. So 1j omega s equals 1j omega. Remember the 1 is because Python doesn't like it having the j by itself. There needs to be some coefficient in front, and GM stays the same. And then under open loop, we have GC times, what am I doing? GC times GP. What is happening? GP times GM. It's getting late. Okay, let's see what happens. There we go. So I need to update the axis here. So are we still in the right figures? Yeah, 6, 7. Okay. So you see we have a dip here since at low frequencies. Again, let me do a split here. Come on now. B, homework B. Okay. Like I said earlier, at lower omegas, our function approaches negative 90 degrees since we're dividing by a very small number. And also remember that tau I is also, since it's a positive number, it essentially acts the same as omega if it were getting bigger or smaller. So same thing there. And then That's why we'll see on the left-hand side, it starts at negative 90 degrees since we have very small angular frequencies. Then as it gets bigger, it climbs back up to that 90 degrees since you're approaching infinity. So it approaches 0 once again. So going back to that, we'll update our axes here. I think it's just, is it range? I think it's range. And then we have to flip the sign since we start from the bottom to the top. So it'll be, let's do I think we did 240 or something in class. 240 to 0. And then a comma. Is that it? There we go. I might have went too far down. So these are all random values, but if we decrease our, maybe I can go a little bit further. Maybe negative 5 to 5. Is that too much? Negative 3 to 3. So you'll see that we actually never hit 180 degrees here. And that's perfect since that's one of the conditions for that instability. So if we never hit negative 180 degrees, it doesn't really matter what our amplitude ratio is, since we never find that, I guess, sinusoidal input that flips and completely wrecks our system. So now what I'm interested in is why our previous transfer functions were okay. So it is dying out, so that makes sense. So there is a sinusoidal input. Again, we are increasing by adding the PI controller. We multiply by amplitude ratio, so there is some chance of sinusoidal input since we're introducing new roots to our closed transfer function polynomial in the denominator. So that's why there's oscillations there. And then we also talk about dampening with second order, so that may also have something to do with it as well. I can kind of see some sort of peak here, perhaps. So yeah, if I believe it's actually, no, that's negative 90 degrees, so that's fine. We can go to 30, so you can see that it's actually negative 90. There you go. So we have a little dip here, and it climbs back up because of omega, explained earlier. And then I want to see how we can get this to be normal. Since it kind of looks like it's unstable, but it's not, it kind of dies out. So let me see. Yeah, it does die out, but after quite some time here. So it's about 20 seconds-ish that goes to 1, which is what we want since that's our step input that we added to our system. Yeah, is that about it for this? And then I want to do the Bode, which is easier for me once I start copy pasting like 3 of these. Yeah, I can try messing around with this. I mean, the whole idea of the second series of problems is that we find the optimum values for Kc and tau I. So again, Kc being the proportional constant and tau I being the integral control. Well, I guess how much we're changing our controller based on the integral portion of that control, the PI controller. So yeah, I think I won't mess around with this, but you'll see that it does die out. So we are still stable and no matter what values. So I wonder if I can make it, if I increase the Kc by a lot, we're more aggressive with our controller and we can never be unstable. So maybe not 1,000 here, maybe 100 back. So, I mean, it is less oscillations. Maybe if I be crazy, bump it up by a lot. Yeah, there we go. Now we're normal. So again, with increasing Kc, so notice that even though I have a stupidly big Kc value, it's perfectly valid since we're never unstable, although we are getting pretty close to it now. About 170. So I'm very aggressive in my control, so it reaches our set point pretty fast within 2 seconds. So that was me kind of messing around with it and guessing, running the simulation. Of course, you wouldn't want to do this experimentally, running all the time and seeing all the different ways your system could screw up with these values of Kc and tau I. So that was just me changing Kc. I could also change tau I. So that's the second part where we find those optimum values. So I'll do this with Bode really quick just to show you that it's not that much different. So let's see. I can just, honestly, I want to copy paste everything. So copy, 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 copy. And I'll go from figure, I didn't copy it, oh my goodness. That, control click, copy. Put it down here, so we're starting at figure 8 now. Hopefully that could copy paste it, I hope so. Yeah, okay, so this will be with Bode. So if I actually do the Bode up here, I think I can just, I need it in the S domain, right? I actually need just these, and that will be replaced here. And these will all go away. And then we have figure, did I say 8? 8. So Bode, let me put it up here just to show you. So Bode, okay, good recording. I don't need this thing. So Bode takes in our transfer function. So open loop, which would be GC times GP times GM. And then it also takes omega, our angular frequencies. So I'll put that there. And you'll notice, shift enter, we get a graph. So it actually gives us our points already, but the figure is kind of screwed up. If you remember from class, if you've watched it, or if you were there. So this figure doesn't actually graph itself. Well, we can try, but I don't think it will if he's fixed it yet. And then we get our amplitude ratios and then our phase lag. So the reason why I know that is because these are negative numbers, and also because he told us in class. But again, these are pretty big, large values going into about the thousands and negative thousands. So that matches our angular frequency, log space points, and then degrees for our phase leg. So I'll unpack these variables to see. Well, we can see if the figure works. I doubt it will. So fig, we call it amplitude ratio, and then phase lag. So let's look at a figure. I don't think it's gonna work. Oh, it's decent. It's pretty close actually. But we have to update the y-axis. So I think that was the thing that we didn't update. So it gives us the points here though. So about negative 173 at 5.7, and you should see the exact same value, 5.7, negative 173. So it's there, but we don't bother using it since the y-axis is kind of broken. So we put an underscore there just to store the variable, but we don't care about it. Now, if I do the exact same thing and put it here where I removed the line of code earlier with getting the real and imaginary, and then separating the real and imaginary from our transfer function in the open loop, as well as doing the amplitude ratio and phase lines of code. So that was the amplitude ratio, kind of taking the magnitude of a vector if real and imaginary were the components of that vector, and then we unwrapped our arctangent since it would shoot up to the positive domain if we didn't unwrap it. So unwrap is from numpy. That's a built-in function that allows a function to keep going down despite the domain of arctangent only ending at normally negative 90 degrees. And then this last portion was the conversion to degrees from radians. So if I replace all of this, let me highlight it, replace all of that with this single line of code for the Bode and unpacked it to have amplitude ratio and phase, we see that's still the same. Yep, 173, 5.7. Yep. And again, for first order transfer function with API controller, we are stable. And I think this is already in the previous video, but for second order, do I have that up here somewhere? We have time delay, which goes to negative infinity, so unstable. For upper bound limit for KC, let's see, 180 degrees, about 15.7. So yeah, we're definitely way over it. We're at already 3. So we had an upper bound of 500 for this one. So it exists, but it was pretty high. But notice that for first order, well, this is second order. First order, we didn't have one since we stopped at asymptotically at negative 90 degrees. Again, that arctangent function. And then I think this was previous stuff. This was our first time, right, with the Bode diagram. Yeah, we had outlet flows. So yeah. Second order, was that graphed? because I think second order just had the peak, right? So second order has a asymptote at 180 degrees again. However, we had a peak, I believe, with our dampening, but I don't know why it's not showing up here. Yeah, I just had to evaluate it twice for some reason. So yeah, asymptote, no matter how far we go, we never hit negative 180 degrees. So technically, it's not supposed to be unstable. However, we have our dampening and the idea that if we had our sinusoidal input, again, this is kind of reiterating from the previous video, but if we had a sinusoidal input from our omega, that angular frequency matching our natural frequency of our system, we would have a height of our amplitude ratio at its max here. So again, the derivative was equal to 0. We did that in the previous video. So if the derivative was equal to 0, we could find that max point, and working backwards, we could find the angular frequency of which this peak occurs. However, with dampening, again, that previous stuff was without dampening. So with dampening, this peak is shifted by however much this factor of zeta is. So usually, well, we talked about overdamped, underdamped, and critically damped. So feel free to revisit that. I think I overexplained that in the previous video. So again, those were the instabilities of first order, second order, and time delay. So time delay had that maximum value of Kc. We had 500 there. Now, PI controller first order were never unstable. So actually, I think I jacked it up at one point, right? That's time delay. I might have changed it. Yeah, let me just try it. I mean, it should fix our oscillations here. So we're being very aggressive with our control. We see that our oscillations die out very fast since we jacked it up so much that we reach our set point almost immediately. So that's the spiel about stability. And then I showed Bode with versus our old method, separating into real and imaginary. Now, I think we can go to the second part here. So let me split like so. I think no more derivations from this point, but we are at the 1 hour. So let's see here. So first order plus time delay. So we just talked about stability. This last portion here was kind of from, oh, you can actually see my cursor. That's cool. Oh, because I'm not on. Actually, I don't know why. Okay, anyway. So this last portion here was actually from the previous video, but I just re-explained it because why not? Now the second portion, what are we doing again? Right, we're doing the optimum values for Kc and tau I. So I can actually do that now, and then we can see how it changes after we do the optimum values. That shouldn't be too hard. We're just multiplying by, or adding in to our process. Technically, I could define another transfer function for time delay, but I'm just going to add it on directly to our process here just to see what it looks like first, and then we'll mess around, try to get it to be stable or reach our set point pretty fast. But there's those optimum values from that ITAE, what was it? Integral time weighted absolute error index. So they found the optimum values, and I'll explain that. Well, I can explain it now. So let me actually just go to it. So with this, what is happening? So with this ITAE thing, what's happened here is that many people have ran many simulations varying the Kc and tau I for different types of controllers. So we have PI and PID. So PID is with the derivative component. We won't be talking about that. We're focusing on our PI controller. So they found coefficients for A and B of the proportional and integral portion of that controller. And we have some footnotes here, essentially equations that allow us to calculate the tau I and Kc. So actually not that tau I, but this tau I for the integral portion, since we're at set point changes. So we use essentially these equations to calculate tau I and Kc given our A and B constants here. And again, these were derived from people, I mean, who knows how many simulations they ran to get a decent, I want to say linear fit, but kind of values to optimize Kc and tau I so that we reach our set point very quickly. And that comes from this idea here. So we have absolute value and that time-weighted portion. So the absolute error comes from where if we have a function, let me go back to our collab here. Right here, we would be taking the absolute value of respect to our, so whatever the value of our function is at its current point. For all the times, we take the difference between that and our set point. So it'd be 1 minus our current value, 1 minus our current value, since 1 is our set point. So we do that for all these points, and then we take the absolute value of those, since positive and negative errors are bad. Any offset is bad, so we take the absolute values of those. And what happens is that we also have this time component, this time-weighted component. You can't see my cursor, whatever. So we have this time-weighted component. Let's do this. Where are we? This and this. This time-weighted component over here, right there. And so this time-weighted component comes from the fact that, well, we have a unit step function, so we are expecting some oscillatory behavior at the start. With a okay controller, like we're not super aggressive. Again, if I change that to like 500, it would be instant, which kind of matches this whole idea of ITAE. We reached our set point very fast, but obviously we're not going to have that 500 valued KC all the time. So we have to, well, an idea is to calculate the optimum value so we don't have to modify it too much to an extreme. So what was I saying? So this time weighted portion. So again, we have these oscillations at the start, since we know we're not going to hit that set point immediately. However, at the end, we have these persistent errors, which we want to, those are the ones that we care about the most. We want to get rid of them as soon as possible. So as they persist throughout this integral, those errors need to get multiplied. Well, they do get multiplied by a higher time-weighted value, a higher t constant, and that allows them to have a greater impact on the controller for this ITAE thingamajig. So that's the whole idea there with time-weighted and absolute error. So now I'll go ahead and code out the code out something, the FOPTD, and then I'll try to see those values. I think we're given them in the problem statement, but we'll try to modify those values how we can before we do the optimal method, which is just some algebra we can do in our collab here. So what's the best way to do this? I think I want to merge these since I don't really care about seeing the polynomial anymore. So I'll merge those. And I think I could just copy these two, right? So I'll copy and copy, paste. So what do we have? Did I paste it already? This oscillation, this oscillation. Okay, so we'll start here. So this will be PI controller with FOPTD, our first order plus time delay. So we already have a first order here. That's not true right here. Our process. So we want to multiply this by E. I think we do exponent since we're in S, right? The Laplace domain. And remember, exponent is from SIMPy here. It's being treated as a symbolic function. So we don't need to type in the np.exp that we usually do. So I'm lost. Where are we? Right here. So we do exp. Actually, I do kind of want to look at it right now after this, so I'll leave a line here. So exp, it was negative theta. So now you know why this theta was here, and I copy pasted and kept it. So negative theta, I believe it's just s, and then don't forget r times k that I deleted. And everything should be the same here. So let's see, it should go to negative infinity. I might have gone too far. And then we can increase the amounts here. So let's go, is negative 3 enough? It might be too much, so let's do -1 and 1.5 like we did in class. I think it was in class, and then we can go further. Let's go 360. So yeah, it gives it a little wider. We can go, how about 3 to 3? Yeah, I mean, this is just going to negative infinity. We can change it to maybe steps of 100. I just want to show that it does go to negative infinity. Okay. anyways, I want to see that negative 90 degrees. So again, that's where we start from. Essentially, we have it's negative 90 degrees from our first order transfer function. We subtract, what was it again? For our time delay, I think it was negative theta omega. So that goes to infinity since omega can be whatever. And then it's just a product of theta times omega. So that allows our phase lag to go to infinity. So remember, first order by itself is just 90 degrees, but then added with that time delay, we can go to negative 180. So now we have a upper bound of our KC. And now with, what else do we have? So we have PI controller. So that is also negative 90 degrees, but well, we have the time delay anyway. So we're going to hit 180 degrees regardless. But remember, if it was just PI controller with first order, we only hit, I mean, we're barely bottoming out here at 170 degrees. So usually it's an asymptote with two first order transfer functions. It's an asymptote at negative 180 degrees. So that being said, now we have upper bound of 180 degrees. So, or from our 180 degrees, I should say. So about 1.8 here, about 1.8. Oh yeah. Huh? Can barely see that. So 1.8 is about 9. Okay, so we are definitely above our amplitude ratio. So if we, I want to look at the our forward loop, since this is in Simpy. Yeah, that's what it looks like. Oh, I mean, I don't know what I was expecting. It kind of just looks the same as everything. Okay. Anyways, so forget the details there. That's not too important. But now, I think, did I run this already? Yeah, we have oscillations, but it is not dying out yet here. So that is because I did not add our EXP. So actually, I don't even need these because they're still in low pass domain up here. So actually, I could delete these. Feedback control, we still need that since it's closed loop. So I can delete that. And now it should work. So let me, are we still Fig 8, Fig 9 here? Fig 9, just to not overwrite everything. So yeah. Yeah, we're not dying out here. That is interesting. We should be exploding given this KC value of 1 and this tau I of 0.01. And then, well, with those values we have at negative 180 degrees, about 2.1. Yeah, we're definitely above the amplitude ratio of 1. So this should be unstable. I'm afraid I am missing something here. Let's see. We just run these two again, maybe. What is happening? There we go. So I don't know if that was actually much different. Do we reach a set point? We do. That is odd. Let me check our parameters. Maybe I'm putting in something wrong here. So we have, what is it? Gain of 1, time constant of 1. Oh my god, I'm using tau. How am I doing that? Does that even matter? We should still be well above. 3.27. Yeah, we're definitely above at like 8. And run this again. There we go. Now we're exploding. It was a tau. I don't know what the tau was before. So let me just double check the constants here. So K is 1, time constant 1, gain of 1, time delay of 0.1, our dead time, optimal PI controller. Yeah, KC and tau I is what we're going to be using with all these thingamajigs. This equation for the optimum proportional gain, or yeah, constant, and then tau I, our integral controller portion. So that was it. That was nice to know. So I guess I deleted, the thing I deleted earlier is because we were in the Laplace domain already. So there's no need to write this again since it was already right here when we use the Bode method, which again is just replacing lines of code. So I could just write that again. So let me just run everything here and let's go to the end. So yeah, we are definitely exploding. We're at to the 25th. So let me go even smaller. Yeah, there you go. Oscillations galore because again, negative 180 degrees. I think we were at like, so that's 3.27 angular frequency. I already forgot the number. 3.27, 3.2, where are we? 3.2, yeah, 8.9 amplitude ratio. So it's definitely over 1. So we are unstable, as you can see from our function. Now we can try to do this manually, where since we're already unstable, we could try to modify this. Let's try 1. I'm just guessing. I don't even know how this works. Oh, that works. Okay. That was surprising. So changing the tau I, so that's 1 over 1 now over s. So this tau I in that integral, remember it was for the integral portion of the PI controller, it was 1 over tau I s. So now it's 1 over 1 times s integral error. So it would just be error times our time. So for some reason, not sure the details there, but we got lucky and chose the right value to modify. About 15.1-ish. Oh yeah, we're definitely under 1 here. So it looks like by a factor of kc, we still have room for about 10 since this shifts up by 10. So if I shift this up by 10, let's see. Are we unstable now? Yeah, we are. Well, it's continued oscillation. Technically stable since we're oscillating around a set point. But let's see, what does our Bode plot say? Our Bode plot says about 15 to 17. Oh yeah, we're still 15, 17. Wow. Oh, so actually I had 2 orders of magnitude left still. So if we want to get crazy, here's where it should go crazy now. So 180 degrees is something around 15, 17 still. So that didn't change. The crossover frequency didn't change. But 15 to 17, yep, is now well above our amplitude ratio of 1. So now this is crazy. Now we're going to the 1/13th power. That's awesome. And with only 100, so let's see 10. Yeah, it just dips about. Is this 5 billion? That's funny. Okay. Anyway, so enough messing around. That was me just messing around with the controllers to see how far we could go, how crazy it would be. So I think KC was 1, and then we had 0.01. Actually, these are going to go away anyway, so I don't even need to remember changing them. So I didn't change these upper values, but now we will be calculating the optimum values given our, what happened? Our OneNote here. So let's see. Do I need to write out algebra? I think I can do the algebra in code. Trying to be cool. Okay. So let's enter in our, so we have A and B coefficient, or I guess constants here. So I'll represent them as we did in class. So PA, BB for our proportional control, and IA and IB for these integral portions. So I can write them, be fancy here, put them in a list, PA, PB. Not really a list, but in series, I don't know the right word. So 0.586, right? And then what else we got? Negative 0.916. And IA and IB 1.03 and negative 0.165. So what we are assuming to get, I did this earlier, so something like this, but instead of oscillations, we will hit our set point faster, essentially. So was this with, this is just first order, so I want to do this with time delay. Could I even hit an oscillation? Oh, let me run this again without everything, just to see what it looks like without optimum values. So we have an oscillation there. With our optimum values here, we should hope to see for our actual function to reach the set point extremely fast without this trade-off for oscillations at the start. Since, again, with an aggressive KC, we hit our set point a lot faster. So right now it's about, I don't know, 4.3. I know I have a limit of like 100. So let's see if this 5 does anything. So 5 does do something. So about 4.3, and now we're at like 1.3 seconds. So again, we have a higher deviation. However, we hit our set point a lot faster with an aggressive control. So we have a trade-off there. Now, what we hope to find is that, well, I guess it wasn't even a higher deviation, but you had an oscillation earlier. So again, with our optimum values, what we're hoping is to see that it hits our set point a lot faster with less oscillation. And that was just with KC. This optimization also applies to tau I. So we'll be using right here. So I entered I just hard coded those in. I mean their values, and now we'll be using the equations. So this design relationship for achieving KC, we have this Y equation. So this is our A constant and B constant, and then we have theta, our dead time. All of those are given here, and then tau, our time constant, system time constant. Then we relate those to an equation y, where we'll have to divide y by k to get our kc. So you can't actually see. Am I even erasing this? Oh, I erased too much. Anyway. Yeah. So we'll type those in essentially, and then we can isolate kc to get the value for kc without having to keep on running these simulations over and over, trying to see what changes and go crazy. So same thing for the tau I. We have another equation relating A and B, and we have all of those. We just need to isolate tau I. So it would be tau over this right-hand side, and that would be our tau I. Well, let's do that. I shift enter here. Oh, I did. So we have, I think I just put it all up here. It can all be down here, so it doesn't need to be run separately. So something like that. Then what do we have? So first one, design relation y equals. So this is for our proportional controller. We have y equals a. Can I zoom in on this? It's so blurry. I hope that's okay. So y equals, go even closer here. I hope you could see this one too. So y equals a, we have that, but this is PA for our proportional controller. Times, we have theta, we have our tau, and we take this to the b power. So this is actually PB because our proportional, that's the design relationship. And we had KC is just Y, so Y over K. So we have the Y and we have our system gain. Pretty easy. Next is for set point changes. So there's that B footnote. I don't know if I mentioned that. So that we have to use this equation since we have a set point change. The integral mode is what it says it is. So tau over this right-hand side. So we have tau over a, let me put parentheses, a plus b times theta over tau. And since we divided by the right-hand side, what's happening? Oh, goodness. Theta over this right-hand side, we move tau I to the other side, so it's tau I is equal to that. Tau I equal to u. Okay. And well, I put a and b, but again, for our integral, we have to put IA and IB. So those were different constants. Again, coming from up here, I just named them accordingly. So PA, PB for these two values. You can't see my cursor. Something like that. So PA for this value, PB for this value, and again for the integral portion, same thing, IA and IB. So hopefully I entered those right. 1.03. Yep. Okay. So let's see what this looks like. We got the ideal values or optimum values. We'll move this there, move this. Let's see. Wow, that is a lot better. We reach it, no oscillations, and we reach it pretty fast, within 1 second, about. I'd say about within 2 seconds. So that's pretty good. I remember earlier we had oscillations. This has no oscillations, and we reach our set point extremely fast. So pretty good. No need to mess with these experimental values. I don't know why I'm so zoomed out. But let's see, are we still unstable? We should be at some certain point. Well, actually, we're stable now. That's what I should say, since we're not blowing up. So 15, yeah, 0.3. So pretty close, actually. But close enough that it doesn't matter since we're at that optimum value. Again, people ran these simulations and they found the optimum values to get those equations for what allowed us to have a Kc and tau I to achieve a very fast set point without oscillations. So believe back to the problems here after a very long time. Here we go. I think we're done. So, yep, that was with our absolute, not absolute, but our optimum values with the closed loop response. So again, that bottom graph was the, I don't know why I'm using this. That bottom graph was the closed loop response since we were in a simulation. And then this was the step change. So, oh, okay, what am I talking about? Make a plot of the Bode diagram showing the calculated control parameters lead to stable closed loop response. So technically, Bode diagram is the forward direction, but it allows us to see that from the input that the closed loop response would be stable. Again, negative 180 degrees, and with that omega, and that omega at our amplitude ratio was not at 1, so we were fine. Though we were skirting, well, relative to the rest of our graph, but in reality, I think it was like 0.3, 0.03. I think it was 0.3-ish, so pretty close, but not close enough to be unstable. And then we hit that point pretty fast in this other plot describing here in response to that step change. So that was the simulation of the closed loop response. I think we're done here. So yeah, again, PI controller. Overall, our overview, that was something new. In addition to our proportional controller we used to do with this idea of a reset time, tau is, tau is, and we did the amplitude ratio. Oh, actually, we did final value theorem first, so we took the Laplace, showing that it was equal to 1, so we did reach our set point, which we've seen multiple times now, versus our proportional controller, which we could not reach a set point, or our set point, because it was the same values over 1 plus the same value, so kck, I think I wrote it somewhere earlier, but kck over 1 plus kck, which would never result in achieving our set point, because with how we derived it through the final value theorem in a previous video. Next, we did our amplitude ratio and our phase lag, which we saw was actually the same as a first order transfer function, except angular frequencies were, and also, well, tau I was where the value of tau I is analogous to omega, since they're both positive numbers. Though in this case, angular frequencies could be negative with our log space that we defined earlier in the code. However, with smaller and higher omega values, we observe these two phenomena of 0 and negative 90 degrees being the domain of this arctangent from this phase lag. So if we added it to our first order, we wouldn't bottom out at we would bottom out at 180 degrees, but never reach it. So where did we stop? I think here was our, I did it with the Bode, right? Or I did it with the real and imaginary. So again, just an overview. So we could never reach 180 degrees, though we were getting pretty close. I did it with the Bode just to show that it replaced, where is it? These lines of code. So we couldn't get the figure working since it was missing the axes. So we just reused the same lines of code for graphing. Next, oh yeah, we had these graphs to represent the actual closed loop response. Again, feedback response, closed loop, same thing. So it was forward direction over 1 plus the open loop. And then we did the first order plus time delay with a PI controller. And then we set the optimum values from that ITAE index, calculated from those equations and constants. And we found that we could reach our set point very fast without oscillations compared to something like this, which is actually a completely different transfer function. But hopefully you get the point there. Yeah, so this has been, I think this is the last video we have for this series. So yeah, thanks for watching.